The moment you flip a light switch, turn on your television, or plug your phone into a wall charger, you are tapping into the largest and most complex interconnected machine ever constructed in human history, spanning millions of miles of high voltage wire, giant magnetic transformers, and roaring turbines across entire continents. But if that raw, pulsing energy generated at the power plant hit your house directly, it would instantly vaporize your electrical panel, melt your copper wiring into liquid metal, and blow your walls apart in an explosive flash. The only reason your toaster doesn't explode when you push down the lever is because of a brutal, highly engineered chain of voltage step-downs, physical magnetic air gaps, and automated safety defenses working silently every millisecond of the day. To understand how that power actually reaches your kitchen table without destroying everything in its path, we have to start miles away at the roaring heart of the energy grid. Inside a modern utility power plant, whether it is running on natural gas, coal, nuclear fission, or massive hydroelectric dams, the core objective is almost always the exact same mechanical trick: spinning a massive copper coil inside a powerful magnetic field. As heavy steam or rushing water spins the turbine rotor at thousands of revolutions per minute, electrons inside the copper windings are forced into motion through electromagnetic induction, generating alternating current electricity typically between 13,000 and 24,000 volts. Now, 20,000 volts sounds like an enormous amount of power, but if power companies tried to send that electricity across hundreds of miles of transmission lines at that voltage, virtually none of it would actually make it to your city. That is because of a fundamental law of electrical physics. The resistance of long metal wires generates waste heat proportional to the square of the electrical current flowing through them. If you try to push millions of watts of power through hundreds of miles of aluminum cable at medium voltage, the massive amperage turns the entire power line into a giant electric toaster element, burning off all your valuable energy into the sky before it ever leaves the county. To solve this, the electricity immediately leaves the generator and enters the power plant's high-voltage step-up substation, home to massive oil-cooled transformers the size of a two-story house. Inside these steel tanks, primary and secondary copper windings wrapped around a laminated iron core use magnetic flux to do something incredible. They drastically jack up the electrical pressure, boosting the voltage from 20,000 volts all the way up to staggering levels like 230,000, 345,000, or even 765,000 volts. By boosting the voltage that high, the required current drops to a tiny fraction of its original flow, allowing massive amounts of energy to glide across hundreds of miles of open countryside with minimal heat loss. Once the electricity is boosted to these extreme pressures, it flows out onto the iconic high-tension sky highways. Massive steel lattice transmission towers marching across mountains, rivers, and highways. If you look closely at these giant towers, you will notice that the aluminum conductors never actually touch the steel frame of the tower. Instead, they hang suspended from long strings of grooved porcelain, glass, or polymer insulator bells. Because hundreds of thousands of volts of electricity will happily jump through several feet of open air to find a path to the ground, these insulator strings create a long, winding physical barrier that prevents lethal arc flashes from jumping into the grounded steel tower. On humid or rainy afternoons, if you have ever stood beneath one of these high-voltage transmission lines, you probably heard a distinct sizzling, buzzing hum. That sound is corona discharge, which occurs when the intense, localized electric field ionizes the surrounding air molecules, creating tiny, crackling microarcs in the atmosphere. As this high-voltage highway approaches your metropolitan area, the electrical pressure is far too dangerous to enter residential neighborhoods, so it makes its first major deceleration at a bulk transmission substation. Here, giant step-down transformers drop the voltage from hundreds of thousands of volts down to sub-transmission levels, usually around 69,000 to 138,000 volts. But managing this much raw power introduces a massive hazard. If lightning strikes a line or a transmission tower collapses, you cannot simply open a standard mechanical switch to cut the power, because pulling high-voltage electrical contacts apart creates a blinding plasma arc hotter than the surface of the sun that will burn straight through solid steel. To solve this, substations rely on specialized sulfur hexafluoride, or SF6, gas blast circuit breakers. When an emergency fault is detected, high-speed pneumatic springs yank the contacts apart inside a sealed chamber while blasting dense SF6 gas directly across the arc, cooling and quenching the plasma fireball in less than 40 milliseconds before the equipment melts. From the transmission substation, lines branch outward into local distribution substations located right inside your town or neighborhood. These are the fenced-in facilities with gravel yards, metal bus bars, and cooling radiator banks that you drive past every day on your way to work. Inside the distribution substation, large transformers step the voltage down once again, this time to standard neighborhood distribution levels, typically between 4,160 volts and 13,800 volts. The substation also houses automated voltage regulators, which constantly adjust the output up or down by switching internal transformer taps to make sure the voltage stays rock steady, even when millions of people turn on their air conditioners at 5 o'clock on a scorching summer evening. You will also find automated switches called Reclosers mounted at the substation exit. When a tree branch momentarily brushes against a power line in a windstorm, the recloser quickly trips open and then automatically closes back up 3 times to clear the temporary fault, which is why your lights often blink several times before either staying on or going out completely during a severe storm. These medium voltage distribution lines then head down your street, carried either on top of wooden utility poles or buried inside heavy PVC conduit beneath the sidewalk. But 13,000 volts is still more than 50 times higher than what your household appliances can safely handle, so the grid requires one final, critical transformation right outside your front yard. If your neighborhood has overhead power lines, you will see a round, gray cylindrical canister mounted near the top of the wooden pole, often called the pole mount distribution transformer, or if you live in a newer neighborhood with underground power, you will see a square green metal box sitting out on the grass. This pole transformer is an absolute masterpiece of electromagnetic engineering. The 13,000 volt primary wire enters through a high voltage porcelain bushing at the top, passing through a primary coil submerged in non-conductive mineral oil that dissipates internal heat. Through mutual magnetic induction across a shared iron core, the transformer steps that high voltage down to 240 volts. But instead of just outputting 2 simple wires, the transformer's secondary coil is tapped right in the dead center, creating a center-tapped neutral wire. This split-phase design is why North American homes have access to 2 distinct power levels from the exact same transformer. Measuring the electrical pressure from one outside hot leg to the other hot leg gives you a full 240 volts, which is what your heavy-duty appliances like your central heat pump, electric water heater, oven, and clothes dryer consume. But measuring from either individual hot leg to that center-tapped neutral gives you exactly 120 volts, which powers all your standard wall outlets, lamps, computers, and phone chargers. From the pole transformer, 3 twisted wires, 2 insulated black hot conductors, and 1 bare aluminum neutral support cable make the final leap to your house in what electricians call the overhead service drop. The wires attach to a sturdy mast head on your roof called a weatherhead, which uses a downward curving hood to keep driving rain from entering the conduit pipe and travel downward along your exterior wall directly into the utility electric meter. Inside this weatherproof metal socket sits your electric meter, whether it is a classic analog model using magnetic eddy currents to spin an aluminum disc or a modern solid-state digital smart meter broadcasting your hourly kilowatt-hour consumption back to the utility company via encrypted radio frequencies. Once past the electric meter, the power passes through the exterior wall and enters your home's main service panel, landing on the massive lugs of the main 200-amp circuit breaker. This main breaker acts as the master emergency gatekeeper for your entire home. If a catastrophic short circuit occurs or you try to pull more than 48,000 watts of total power at once, the internal bimetallic strip and magnetic coils trip open, completely disconnecting your house from the grid in a split second. From the main breaker, power is distributed across 2 vertical copper bus bars, branching off into dozens of individual 15-amp and 20-amp circuit breakers, feeding the insulated Romex copper wiring buried inside your drywall, running all the way to the light switches and outlets in your walls. What makes this entire global machine truly astonishing is the delicate balancing act happening behind the scenes every single second of the day. Unlike water or natural gas, electricity in the grid cannot easily be stored in massive quantities. Every single watt of power being consumed by your refrigerator right now had to be generated by a spinning turbine hundreds of miles away just milliseconds earlier. Power grid operators must constantly balance total electricity generation with total consumer demand to keep the entire system vibrating at precisely 60 cycles per second, or 60 hertz. If millions of people turn on their appliances simultaneously and power plants cannot ramp up production fast enough, the increased electrical drag physically slows down the massive steel turbines at the generating stations, causing the grid frequency to drop. If that frequency falls by even a fraction of a single hertz, automatic safety relays across the country will instantly begin shedding entire cities from the grid in cascading blackouts to prevent multi-million-dollar generators from ripping themselves apart. So the next time you plug in your phone, brew a pot of coffee, or switch on a reading lamp, remember that you are not just drawing power from a quiet socket in the wall. You are reaching through hundreds of miles of aluminum wire, tapping into massive oil-cooled magnetic transformers, and drawing instant energy from roaring generators across the continent, perfectly balanced and tamed down to the exact millivolt your home needs to keep the lights burning bright.